When the buoy is at equilibrium, its weight mg acts downwards, and the buoyancy b0 acts upwards. By Newton's first law, we know that these forces must balance, so b0 is equal to mg. When the buoy has been displaced by a displacement of x, its weight of mg still acts downwards, but the buoyancy force b upwards is different. In order to calculate the buoyancy, we need to use the fact that the cross-section of the chimney is an area A. Taking upwards as positive, from Newton's second law of motion, we know that the resultant force is equal to the mass times the acceleration. This gives b minus mg is equal to ma. From Archimedes' principle, we know that the magnitude of the buoyancy force is equal to the weight of the water that the object displaces. When the buoy is in its equilibrium position with a volume v underwater, this means that the buoyancy b0 is equal to the density of water, rho w, times by the volume v times by g. When the buoy has been pushed down by a distance x, the volume underwater v dash is v plus a times minus x, because we're taking changes in x upwards as positive. And so if the buoy is displaced downwards, increasing the volume in the water, then x is negative, and so a minus x will give you a positive additional volume. This gives us the buoyancy force B is equal to the density of water times this v dash times g, which is equal to the density of water times g times v minus a x. You can now combine these to get an SHM equation of the form x double dot is equal to minus omega squared x, and then you can work out the time period of these oscillations using the equation t equals 2 pi over omega.